what determines the color that you see of light, red, purple, whatever, is the frequency. Okay, and this is going to be important. It's the frequency, not the wavelength. So, and here's how you can show this. Is that, so I've got my handy dandy laser, right? Okay, and I shine it through the glass. Oh, shine it through the glass, okay? And it shows up on the wall up there, right? Now, even though it's going through glass and it's slowing down, so I'm altering the wavelength, which I'll show you in just a second. But the frequency stays the same. Because if the frequency changed, increased or decreased, then I would change the color of the light, okay? So, which is kind of cool, because it isn't like, and thankfully that works that way, because if I change it as if light went through a lens, and it changed the energy, then like I would look at, you know, a red shirt, right, without my glasses, and it would appear red. But if I put my glasses on, and then that energy changed, then that shirt might change into, you know, a different color. So it'd be like red, oh, green, red, green, okay? And so thankfully, we change the wavelength, but we don't change the energy. Yes?
So if light passes through like glass and the wavelength changes, it doesn't change back when it...
It does,
Okay,
but the frequency never changes.
okay.
Okay? Yeah, the wavelength expands and contracts. And again, just accept it.
I mean, even if it did change, even if the frequency did change the glass, it would probably change back once it came back out.
Yeah. Okay. So here's the deal. So if you look at what's on this, this is what's called the index of refraction. Okay, and this is this letter N. So this index of refraction is a ratio of the speed of light in a vacuum to the speed in the material. So when you hit water, diamonds, whatever, it slows down. So obviously this is the speed of light in a vacuum. This is as fast as it can get. So if you divide by a number less than the speed of light, what's going to happen to that value of n? Will it be bigger than 1 or less than 1? Bigger than 1. So your value of n, okay, if you have an index of refraction of 1, that basically means that the speed in the material, which is like air, is the same as the speed of light. Okay? So index of refraction of air is usually rounded to 1. Technically it's like 0.999, okay? It's basically 1. So, but like diamonds, glass, different optically dense materials have different values. So here's how you can look at this in terms of wavelength. So c is just the speed of light. So that would be the frequency of the light times the wavelength of the light in a vacuum, and that would be divided by the frequency in the new medium times the wavelength in the new medium. So, what happens is that these frequencies don't change, okay, which is why the colors don't change, okay, because the energy stays the same. So since these values here are the same, we can drop those out. So this also becomes n is a ratio of the wavelength in a vacuum to the wavelength in a new material. So again, the only way that you can get an n bigger than 1 is if the wavelength in that new material is less than the wavelength that's in the vacuum. Okay? Makes sense?
Yeah.
So the bigger your value of n is, the bigger the discrepancy between that wavelength in a vacuum and that wavelength in that new material. Okay? Makes sense. So sometimes you'll see this written, it's the same thing, but a lot of times what you want to solve for is that wavelength in that new material, and you just solve for that, and it's like the wavelength in a vacuum divided by n. So, like let's say for example, you're told that the index of refraction is like 1.35 and you're asked to find the new wavelength. So you take the wavelength in a vacuum divide it by that index of refraction, boom, there's the wavelength of the new material. And again, so the bigger this becomes, the smaller that becomes. Got that idea?
Yeah.
Okay. All right, so this is going to be important. Wavelength becomes shorter the more optically dense the material is. Okay? And then once you get out of that, then it expands. Okay. Now, if you want to zone out for just a second, I got to draw a fairly complex drawing. So if you want to stand up and stretch, stop that for a second because